All right, let's just do examples from now on, because I think just going through the process just helps you understand the concept. So before we get started, in one of the slides it says Excel cheat sheet. I posted this, and it basically is giving you a cheat sheet for Excel in terms of the functions that you can use to calculate the critical values and the p-values, right down here, critical values and the p-values for both z-test and for t-test for population means, right? Or this still applies for population parameters as well. So for the critical value, right, if you have a one-tailed test or a two-tailed test, and then for p-values for one and two-tailed tests. So this is there. Note that this is for, like, when you see 0.05 and 0.025, obviously this is for alpha of 0.05. But if you have 0.01, right, you would just substitute, right, those numbers appropriately. But everything else should be the same. So let's do an example. Use of texting. So text request reports that adults 18 to 24 years old send and receive 128 texts every day. Suppose we take a sample of 25 to 34-year-olds to see if their mean number of daily texts differs from the mean of the 18 to 24-year-olds. State the null and alternative hypotheses we should use to test whether the population mean differs for these two populations. Suppose a sample of 25 to 34-year-olds showed a sample mean of 118.6 texts per day. Assume a population standard deviation of 33.17 texts per day and compute the p-value with alpha of 0.05, level of significance. What is your conclusion? Repeat the hypothesis testing using the critical value approach. Okay, so in this we are dealing right with a population mean, and we do know the population standard deviation, so we know, right, what type of test is this? It's a it's a one sample z-test, right, because we know the standard deviation of the population. Then the next question is this a one or two-tailed test? Right, what do you think? It is a two-tailed test because we're just looking to see if they differ, right, to see if they're more or less than the 128. We're not saying that, hey, the 25 to 34-year-old age group, did they text more or did they text less? We're not asking that. So there's no greater than or less than involved. It's just, do they differ, right? Does it equal 128 or does it not? So that's how we know it's a two-tailed test. So let's go to Excel. Escape, and I think you should be able to see this. I'm trying to get better with the videos in terms of making them large enough so that you can see them, because I know the video quality is not as great sometimes when I record compared to what I see on my screen. Okay, so right, population mean, standard deviation. No, this is already the solution I have here, but we're going to do it together. Right, so what are our hypotheses? Right, the null in words would mean that the mean number of text does not differ for these two groups. The alternative is that they do. In terms of numeric numbers, right, we want to say the null is that they're the same, right? There's no difference. So mu should be 128. The alternative is that they are, that the average is of the population is not 128, right? And because we're dealing with equal signs, we see it in the hypotheses, we know it's a two-tailed test. So let's go through the information that we know. Mu, right, is 128. That is the population parameter for the other age group. And then we're comparing it to our sample. What's our sample? Sample mean of 118.6, 118.6. Right, we're just kind of writing down our known information. What is the population standard deviation? That's given to us somewhere, 33.17. Right, and what is n? That's given to us as well. A sample of 30. Right, so I think now we have most of our information. I think what we do know, alpha is 0.05. So now we can go ahead and calculate some of the information. Right, we need the standard error, right, which is equal to the population standard deviation divided by the square root of n. Boom, that's our standard error. So with our standard error, we can calculate, right, our z-score. So our z-score is x bar, right, minus mu, the difference between our sample and population parameter, divided by the standard deviation, which is the standard error, right? The standard deviation of the sampling distribution is the standard error. Okay, so that's our z-score. Right, we can do a couple different things. We can compare this to a critical value to determine if we reject the null or not, and that's actually part D, right? Use the critical value approach. But let's just do this because we just calculated z, so let's see what happens. So remember, for this, we are trying to calculate the critical value, right? Is a two-tailed test. So remember, we're giving Excel the probability, right, in order to tell us the z-score. So we know which function do we use. Norm equals, right, S dot inverse or distribution. Remember, the distribution is given to give us a probability distribution, so it's going to give us a probability. We don't want that. We want to give it a probability and tell us z. So we know we're going to have to use the inverse function. So it's telling us what is the probability. Well, remember, we're dealing with alpha as 0.05, but it's a two-tailed test. So we have to divide by 2, right? So 1.95. So that's our critical value region. So we look at our value, 1.55, and it does not exceed that. So because it does not exceed that value, right, we fail to reject the null. So that's our answer right there. So in terms of what is your conclusion? Well, we can conclude, right, we fail to reject the null, so we can basically say that the average number of texts is basically the same for these two groups. So let's go on, let's calculate our p-value. So for our p-value, yeah, this is where we are going to want to calculate our probability. So it is equal to the norm.s.distribution function. It takes two arguments, z, so we have to give it our z-score, and cumulative is true. So this is going to give us the probability under the curve up until negative 1.5 standard deviations, right? So that's 1.55 standard deviations below the mean. So it's going to give us the area under the curve, right, to the for that tail to the left of the distribution. So that's our p-value. But remember, it is a symmetric distribution, and this is a two-tailed test, so we actually have to take that value and multiply it, right, by 2, because it's a two-tailed test, right? So did that make sense? So actually go back to an older slide that we looked at in terms of the two-tailed test. Remember, we were talking about the golf ball example, right, when we just said that, you know, it's non-directional. So this is exactly what happened. We calculated our z-score. It's actually pretty close. Wow. It was negative 1.55. So, right, this was, right, it's negative 1.55 as the z-score, so that means it's 1.55 standard deviations below the mean. So when we ask for the probability, it's giving us a probability under the curve up until that point, right? Cumulative is true, so if this is a whole cumulative distribution, right, it's only giving us the area up until this curve. So that's what is being calculated, the probability or the area under the curve right there for that region. But remember, we want to know the p-value. Because it's a two-tailed test, we need the probability for both, right, regions under the curve, because it's a two-tailed test, right? So we want the area under the curve for both tails, right, two tails. So we have to take that value, that probability we calculate, and multiply it by 2. So it's basically what we're doing is we're adding this probability, right, and this probability together to find out the total probability, or total p-value. So, right, that's what we're basically doing. Just doubling this value, and that is our p-value. So again, if we're comparing this to 0.05, right, our number is not less than 0.05, so therefore, again, we fail to reject the null, and we come to the same conclusion. So that's really all there is to that example. So in terms of our cheat sheet here, right, is a z-score, right, for our critical value. It's a two-tailed test, right, so we use the norm.s.inverse function. Remember, we used that right here to calculate the critical value, right, norm.s.inverse, right, and then I wrote in here 0.025, but that's the same as 0.05 divided by 2, so we use that. And then for the p-value, remember we calculated it for a two-tailed test, so we took that value using the norm.s distribution, right, z, we gave it the z-score, true, and we multiplied that by 2. So that's mostly that. In the next video, we're going to do another example, but with the t distribution.